Okay, so this is a continuation. We're going to finish up our section 11.3. We got as far as discussing how we can kind of find this remainder, which is a really good sense of how good our approximation is using the integral test. Because remember, using the integral test will not give you the exact sum, but we can make it really close by making our remainder really small. So that's the general idea. And we discussed how to actually come up with the remainder, depending on if we do an over or an under approximation based upon a left or right Riemann sum. Excuse me. And you can see that a left Riemann sum would be a slight over approximation and a right Riemann sum would be a slight under approximation, given the fact that we need to start with the n+1 term. So let's take that into the next page and actually do an example on how we can determine what our remainder is. Okay, so our job here is to approximate the sum of the series 1 over n cubed as n goes from 1 to infinity using the sum of the first 10 terms. So we're going to approximate the sum of 1 over n cubed only using the first 10 terms. So really this should kind of say part A or question A right there, and then this right here is question B. So the first thing, well, not question A, statement A says estimate the error involved in this approximation, and then part B says how many terms are required to ensure that the sum is accurate to within 0.0005, or what is that, tens, hundreds, thousands, 10,000, to within 5 10,000ths. Okay, so the first thing that we need is we need to actually figure out an estimate for our remainder. Now, technically, you can use whichever remainder that you want. It's going to be much easier to use the integral from n to infinity as opposed to the one from n+1 to infinity. This will give us an estimate of the remainder, so we need this. So we need to figure that out for our function. So up here, we're going to let f of x equal 1 over x cubed. Okay, so we're going to let that be our function so that we can do this estimation. Well, if I'm going to take this estimation for our remainder as the integral from n to infinity, it's improper, which means that we need to do an improper integral. So let's take the limit as t goes to infinity of the integral from n to t of f of x, which in this case is 1 over x cubed dx. Then we're going to perform this just like we would any other improper integral. So we'll have the limit as t goes to infinity, antiderivative of 1 over x cubed, which is the same thing as x to the -3. So if we raise that power by 1, we get x to the -2, and then we divide by -2. So really we get -1/2 x to the -2, or -1 over 2x squared. Okay, I'm not going to write that whole thing out, but that is the antiderivative. Change the 1 over x cubed to x to the -3. You'll see that this is what we get. We evaluate that from n to t. So then we're going to have the limit as t approaches infinity. Using the fundamental theorem now, plugging in t first, we get -1 over 2t squared minus -1 over 2n squared. Remember, n represents an integer. It's some kind of a number. So as t approaches infinity, that first term, -1 over 2t squared, is going to go to 0. Then you have minus minus, which becomes plus. There are no t values in that 1 over 2n squared, so it's just like having a constant. So our eventual limit there is 1 over 2n squared. Okay, that right there represents our remainder. But it says estimate the error involved in the approximation. Okay, so part A. Now let's actually move on to do part A, because we needed this in order to do all the rest of it. We needed some kind of an expression for our error. Well, it says using the first 10 terms, estimate the error in the approximation. So really what I need is I need the sum, as n goes from 1 to infinity, of 1 over n cubed. We want that to be approximately equal to the partial sum of the first 10 terms. So really what you're going to do is you're going to take that sum from 1 to 10, because that'll be the first 10 terms. So that would be, let's see, plugging in a 1, you'd get 1 over 1 cubed. Plugging in a 2, you'd get 1 over 2 cubed. Plugging in a 3, 1 over 3 cubed. We do that all the way up until we get to 10. So 1 over 10 cubed would be our last term. Now, obviously, this is not something I expect you to do without your calculator. And I've already gone ahead and plugged this into mine to save a little bit of time. So we get 1.197531986. That's all the decimals that my calculator spits out for me. So that is our approximation of this sum of the first 10 terms. Well, remember that the remainder is going to be less than or equal to, let's write this down, the remainder is going to be less than or equal to, and this is from the previous page, the integral from n to infinity, which we just found, of f of x dx. Okay, so we're talking about the remainder based upon the sum of the first 10 terms will be less than or equal to the integral. Well, if we're talking about n is 10 to infinity of f of x dx. Well, we've already figured out what our remainder is. We know this integral right here is going to be 1 over, comes from what's in blue, 2n squared. But n is represented here by 10. So it says that our remainder, or our integral, excuse me, is 1 over 200, which means that the remainder is less than that. So the remainder we have bound by the fact that it's going to be less than 1 over 200, which is, in decimal terms, 0.005. So what that's telling us is using the sum of the first 10 terms and the fact that we've already figured out an equation for our remainder, we can just plug the 10 in for n and get the fact that our estimation here is going to be within 0.005 of an estimation. Okay, it's a close approximation. It's not an extremely close approximation, but it's a pretty decent approximation. Obviously, the more terms you were to take, the better the approximation would be. But we're only told to use 10 here. And then part B says, using the same information, how many terms is it going to take to make the approximation within 0.0005? So we're adding another 0 in there. Well, let's see. So we want our remainder of the first n terms, again, to be less than or equal to, I'm just rewriting the same information that I've done before, integral from n to infinity of f of x dx. We want our remainder, this is what we want, to be less than 0.0005. That's what we're looking for. Well, we do have the expression for our remainder, which is 1 over 2n squared. And we want that to be less than or equal to 0.0005. So now we're going to solve this for n. If you were to reciprocate both sides, you're going to get, what is that, 2n squared. Now, if you reciprocate, you actually have to change the inequality symbol. Reciprocating 0.005 is going to give us 1 over 0.0005. And then if you were to divide both sides by 2, you're going to get that n squared is greater than or equal to 1 over 2 times 0.0005, which is equivalent to 1,000. That's what 1 over 2 times 0.0005 is. So then I would have to take the square root on both sides, excuse me, and I would get that n is greater than or equal to the square root of 1,000, which works out to be approximately 31.62. But remember that n has to be a whole number because we're talking about the counters. So really, if n has to be greater than or equal to 31.62, we know that n is 32. So what that's saying ultimately is that it's going to take 32 terms. So it would take an S sub 32, the sum of the first 32 terms, to be accurate to 0.0005. Okay, not a short process to do by any stretch of the imagination, but you definitely need to be able to do the improper integral from n to infinity in order to develop the general form for the remainder. Okay, that is going to be your remainder form. And then you can use that remainder to figure out how accurate you are, how accurate you need to be, how many terms you need, so on. So the question is, can we make this better and easier? And the answer is yes. So we're going to actually take and we're going to manipulate the formulas that we have in the previous page. So let's just write this down. We'll recall real quick that the remainder is the same thing as the entire sum minus the sum of the first n terms. Or solving that for the sum is the same thing as the remainder plus the first n terms added up. Okay, so now let's go ahead and look at the inequality, the inequality that we stated on the other page. So it says we've got the the integral from n plus 1 to infinity of f of x dx is less than or equal to our remainder of the first n terms, which is less than or equal to the integral from n to infinity of f of x dx. Okay, and that's what we developed on the other page. Well, if we replace r sub n, you can do this on your own paper. If you replace that with s minus s sub n, and I actually want to bound my sum, I'm going to add s sub n to all three pieces. Right? I'm going to add s sub n to all three pieces, which gives us ultimately s sub n plus the integral n plus 1 to infinity f of x dx is less than or equal to your actual sum, which is less than or equal to the integral from n to infinity of f of x dx. I hate to put it out here on the end, but I'm going to put the plus s sub n on the end there. So really what that does is it gives you some kind of a bound. This right here would be a lower bound for your sum, and this right here would be an upper bound since it's in between those two. So if we can get an upper and a lower bound, then we can basically just average those two things to get a really good approximation for our sum. So let's see how that works on the next page. So the good news is we found some of this stuff already. We already know s sub 10 because we did it on the other page. If we didn't know it, then we would have to repeat the process. But what we're looking for is we're looking for s sub 10 because that is our sum. Remember the first one on the previous page, what we just wrote, was this was the integral from the n plus 1 term to infinity. Well, n plus 1 here is 11 to infinity of f of x dx. That will bound my sum with its upper bound, which is the same thing as s sub 10 plus, and this one was from n to infinity, so that starts at 10 and goes to infinity of f of x dx. Okay, well, again, we've already found the partial sum S sub 10. I'm not going to write every single decimal out. I'm going to write like the first 5 decimals or something. So it'll be like 1.97532. That's what S sub n is. As far as the integral from 11 to infinity and 10 to infinity, those are the remainders. We have the formula for the remainder, which we have on the other page. And that was, I believe it was, the remainder was 1 over 2n squared. So let's write that down. So n in the first case here is 11 because that's what the bottom value is. So it's plus 1 over 2 times 11 squared. That's less than or equal to s, which is less than or equal to. The next one is going to be our sum for 10, and then from 10 to infinity, again, we've actually done that one, which was 1 over 2 times 10 squared. All right, and then plugging all this stuff into your calculator, because obviously, again, I don't expect you to do any of that stuff in your head. What we get is on the left-hand side here, you get 1.201664 is less than or equal to your sum, which is less than or equal to 1.202532. If you were to take those two sums, add them together and divide by 2 or average them, then your sum, the actual sum based upon our approximation, is approximately equal to 1.2021, and that's going to have an error with an error of less than 0.005. And in this case, we only required 10 terms because we only did s sub 10. We used the 11th term in the integral part, but we only required 10 terms in order to do s sub 10. So that's a lot less than the 32 or whatever it was that we found on the other page. All right, so there is how you do it. And this is not easy, by the way. This is not easy stuff to get straight and remember, so you might have to go back and look at it. The most important one is knowing how to do it this way, believe it or not. While it's a little bit longer and a little bit harder, it is important to understand how to find the accuracy to a specific value by finding that remainder by using the improper integral first. So that's the most important way. All right, but that should finish up how you actually find these errors. This concept is going to be very important the later we get into the chapter.